And we're going to start our discussion of chemistry with talking about matter and change, because essentially that's what chemistry is. Chemistry is the study of matter and changes in that matter. So that's what we're going to be looking at here. And while we talk about chemistry here for a while, is what is matter, and how do we describe the matter, and then how do we look for changes in that matter. But maybe first, what is the matter? Okay, to matter. For you to matter, you need to have two things: mass, and you need to have volume. And all of you have mass and volume, so it's very nice that all of you matter. But everything we look at really is matter. So this is such a broad definition because everything falls into it, except for maybe your feelings. Maybe your happiness doesn't have a mass or a volume. Perhaps it does. Perhaps you have so much happiness that it occupies your whole soul, and then it has quite a bit of volume. But for the most part, we're talking about things that are physical, that have mass, that have volume. But even space. We like to think of space as being an empty vacuum, but really space isn't an empty vacuum. There's tons of mass in space. Now, if we're between, say, stars, if we're between a couple stars here, maybe there's not a lot of mass, but there is particles that are floating around in that space, and it has mass, and it takes up space. It has a volume, and so it has matter. So really, chemistry can be a really broad subject. We can go everything from talking about like subatomic particles that physicists would talk about to talking about reactions that occur in animals and in humans like biologists would talk about. So sometimes it's referred to as kind of a linkage between physics and biology, but really it is it is the sole, perhaps for me it's the sole subject. Don't tell anybody else, but it's probably the most important science subject you will ever study in your whole entire life. Okay, so maybe one of the things we want to talk about when we talk about matter is just the phases that the matter can occur in. So matter, again, the stuff that occupies space, that has a volume and has a mass, can be a solid. And there's some things we should know about defining what these solids are. So solid, and this is talking about a crystalline solid. Don't worry about being a crystalline. This can work for any solid. There's an ordered arrangement. That's probably an important term to have there. So it says there's an ordered arrangement of the particles, and they're essentially, here's a big key word, essentially in fixed positions. There is motion, but they're essentially in fixed positions. Notice, if we heat this up, basically we're adding energy. So we heat this up, we add energy, and those particles start moving, right? And they're free to move relative to the other particles, but still they're relatively close together. So when we take a solid and we change it into a liquid, now let me clean this up a little bit. Okay, so you'll notice I wrote some things. You might not be able to read it, but I did write some things. So a solid, when we think about it, has a definite shape and a volume. A liquid, when we heat up these molecules so they can move a little bit more freely, but they're still packed pretty close together, liquids have a definite volume. Okay, so if you have, like my cup of tea right here, my cup of tea is about a cup of tea, and if I pour it into a different cup, well, it is still a cup of tea, but it has no definite shape. So it has no definite shape. It doesn't have its own shape, but it does have a definite volume. Now again, if we heat those molecules up even further, so there is total disorder, and they move apart as far as they possibly can, then there's no shape, no definite shape, and there's no definite volume. They'll occupy whatever volume is available to them. So notice as we move up these phases of matter, we're moving up. Also, we want to think about this. Sorry, I'm getting a little confusing here. In terms of energy. So these are increases in energy in the particles as well. So what is the difference between water in the liquid state and water in the solid state? Well, how much energy those individual particles have, and thus how much they're moving. So when we think about phases, we want to think about them in terms of energy and motion. And really, we'll talk about this a lot more when we talk about chemistry, but the different phases that we enjoy matter in are really phases of are really relative to the motion of those molecules and how much energy they have. Now, there are other phases that you'll hear about, plasmas. So plasmas would be beyond gas. That's where we've actually removed the electrons from the molecules. But again, at a chemistry standpoint, what we do in class, the three phases of matter is just plenty. We don't need to add a fourth or a fifth. We don't need to add any Bose-Einstein condensates or neutron degenerate matter. because I'm not even really sure what all of that stuff is. The three phases of matter, though, I'm pretty comfortable with, and hopefully you are. These might be some words you want to know, too, just while we're talking about the changes, the phase changes of matter. We might want to know the terms on them, and we probably do. As we go from a solid to a liquid, we have melting or freezing. For a liquid to a gas, it's called evaporation. I like vaporization better than evaporation, but we'll use what they're having here. And condensation to go in the other direction. A solid straight to a gas, these are ones that you probably don't use as much, but a solid can sublimate. That's when a solid goes directly to a gas. And that's what you'll notice, actually, if you have, like, ice cubes that have been sitting in your freezer for a long time. You'll notice that the ice cubes have gotten smaller. And how did that happen? Well, some of the solid ice actually sublimated. And we'll talk about kind of how that happens further on in our time together, and deposition would be in the other direction. Okay, phase changes. Okay, so to define matter a little bit better, all matter essentially is made up of atoms and molecules, and we know what an atom is. Here's a nice little smiley atom. This is a happy atom. An atom is the smallest building block of matter. So atoms are the smallest building blocks of matter. Atoms bonded together, which we'll talk about here in just a moment, make up our molecules, and that composes all the matter that we know. All known matter is made of atoms. So where do we go from there? Well, let's move this up here. Take a look. Oh, get rid of you. So atoms, molecules, they make up all our matter. And again, atoms are our smallest building block of substances. And then bonded together are molecules. But let's look at our chemical breakdown then of matter, because normally when we think about matter, we start right here. We know that everything that we're studying is matter. Our matter can be what we call substances. Also, I actually prefer the term pure substances, or they can be mixtures. A pure substance can either be an element, so this is made up of only one type of atom. So an element of gold, like this is just made of gold atoms, so all these balls of gold stuck together. If we had something else, say copper, it'd just be made up of copper atoms. What a compound is over here is a compound are atoms bonded together, and I'm going to throw in a little bit of a definition here for you. When we think about compounds, these are bonded together in a set ratio. So they're not just atoms thrown together, they are bonded together in a set ratio. So whereas this could be gold, this right here is showing you this is water. Water is H2O. 2 hydrogen atoms, 1 oxygen atom bonded together. That is water. This is salt. It is 1 sodium to every 1 chlorine. And notice it's bonded together in a lattice, but they're bonded together. They are stuck together. There is a chemical bond there. That is a compound. On the other side of our chemical breakdown list here, and I can erase that so it's not too messy, we go over here and we have mixtures. Mixtures can be either homogeneous or heterogeneous, and what mixtures are is they're mixtures. They're non-definite. There's no set ratios. They're non-definite mixtures. Non-definite mixtures. And that's really great to define a term with a term of atoms. So there's multiple atoms and or molecules, compounds, all mixed together, right? So that's what we have. We have a mixtures of atoms and compounds. There is nothing set about it. So what this is taking a look at then is when we look at things that are homogeneous look uniform, but they are not. This is kind of a funny example for something that is homogeneous, but normally we think of something homogeneous being like my cup of tea. So I'm drinking tea a lot right now. If I look at my cup of tea, it looks like one thing, but it is not. It's actually water in there. There's the tea. There's some sugar. I put some sugar in my tea because it makes it taste better. That is a homogeneous mixture, or a homogeneous mixture. Sometimes heterogeneous, it looks like it's multiple things. So if we have something that's heterogeneous, you can see all the different particles. A great example of this is sand or dirt. You go to the beach, you dig up sand, you can see there's different particles. So it's made of different elements, different types of rocks. So it is a mixture. So mixtures have elements and compounds in them, but those mixtures are not physically bonded together. They're not in any set ratio. They're random. Maybe that's the best word for mixtures, is they are random amounts of atoms and elements. Elements and compounds together. I'm sorry that this chart has flipped things around just to make it more confusing. This time mixtures are on this side. Pure substances are over here. Same general chart though. One thing, what I like about this chart that I want to focus on now is that, again, mixtures are variable, they're random, but they may be separated into their pure substances by physical methods. So there's physical ways to separate mixtures down into their pure substances. Now, so mixtures are mixtures. They're mixtures, but they can be separated. Now, if we look at pure substances cannot be separated by physical changes. The only way we can separate pure substances, we can separate compounds through chemical changes into their elements. So actually water, the one compound that we looked at before, can be separated into hydrogen and oxygen by a chemical process, but not by a physical process. So if we're talking about differences in physical and chemical processes or physical and chemical changes, well then we need to know what those are. Okay, so when we're talking about a physical change, so we say mixtures can be separated by physical changes. Well, physical change is a change that no new substance is produced. So what we started with is still there when we end. So typically it's going to involve a change of state, not always by any means. And notice what it said, it can usually be reversed. So physical change, melting ice is a physical change. You can refreeze it, it's ice again. Dissolving salt in water, you can evaporate the water, you get the salt back. Those are physical changes. Now, if we look at things that are chemical, here, let's take a look at some stuff that's chemical changes. A chemical change is when we produce new substances, when the process of testing for the chemical change, or the chemical change itself, produces new things. And so burning is a classic example of a chemical change, because if we burn something, we can't get the wood back really easily, right? We've converted it into something else. We've taken some carbon, hydrocarbon compound, and we've burned it in the presence of oxygen. We've made CO2. We've made water. A lot of times we make some soot when we burn things too, but we've changed it. We can't take that CO2 and water and put it back together and make that hydrocarbon very easily without, again, another chemical reaction. So I guess we can go backwards, but the only way we can go backwards with this is another chemical reaction. Clues that something is a chemical change is a lot of times there's a smell or a gas, a color change. Gas can be formed. Those are clues that we might have a chemical change going on. So probably the easiest way to think about this is just to look at some examples. So this is from a worksheet that we're not going to do because we are just going to look at it. So if we have sodium hydroxide and we dissolve in water, that's mainly a physical change because we can evaporate the water, get the sodium hydroxide back. That's physical. Chemical is anytime we have a reaction. Notice hydrochloric acid reacts with potassium hydroxide to produce a salt, water, and heat. Well, we have new things. That is evidence of a chemical change. We've changed some chemical compounds. Now there's new chemical compounds. That's chemical. Cutting something up is physical. Heating something and changing it into a different phase is physical. Decomposing potassium chlorate into potassium chloride and oxygen gas, that is a chemical change. Notice here, there's a few more. We might as well just look at them because we're on the roll. We're going to get them all. Iron rusting. Iron rusting is you have iron reacting with oxygen to make iron oxide, normally iron 3 oxide. So that has been a chemical change. We've taken elements, we've bonded them together, now we have a compound, that's a chemical change. That we have to have another chemical reaction to break that back down into iron and oxygen. So again, evaporation, ice melting, those are all physical. Milk souring is actually a chemical change going on. You can't get the original milk back. So if you're trying to decide if something is a physical or chemical change, think about how easy is it to go backwards in that process. That gives you typically a clue. Let's just list out some physical and chemical properties, and then I think we will be done. Okay, so most of our chemical properties that we look at are reaction types of things. We are asking, is the compound, does it react in air? Is it acidic? Does it react with an acid? Does it react with a base? How does it change with water? So most often, what happens if it's heated? Does it decompose? Does it change color? So most of our chemical properties are reaction types of things. And we can tell if they're a chemical property because we're going to look for things happening, like changes. This delta symbol means change, and I'll use it quite a bit. So changes in color, or changes in temperature, or changes in state. That means like if we make a precipitate, or if we make a gas when before we did not have a gas. These are evidence of chemical changes, and evidence that we might be testing some chemical properties. Another thing is when we test a chemical property, we actually destroy what the compound is, so we can't get it back. So if we are testing, if something's flammable and we burn it, well, then we can't get it back. So testing for chemical properties changes what we're testing. On the other side, if we're looking at physical properties, physical properties can either be intensive or extensive. Intensive means in, right? And extensive means, well, they're outside. So intensive properties are how we test physical properties typically, because our extensive properties, they depend upon the amount. That's how massive something is, how long it is. Well, that depends on how much of it you have. But if, say, you have a piece of gold, and that gold has a certain amount of mass, well, if you cut that gold up, it's still gold. It might be smaller. It might have less length, less mass, but it still is going to have the same color, the same tasty gold taste, the same melting and boiling point, density, luster, hardness. Again, these are all things that can be tested for without destroying what it is. I mean, obviously, you might have destroyed your ring if you're melting it down to see if it is gold, but you could freeze it again and make solid gold. Density is the big intensive property that we use a lot, actually, for identifying what substances are. But our intensive properties, one thing we want to say about our intensive physical properties is they help us help us identify what the compounds we are looking at are. So these are the big ones that we're going to use. Chemical properties, intensive physical properties are going to help us identify what things are, whether they're elements, whether they're compounds, whether they're homogeneous or heterogeneous. Again, homo or heterogeneous things are not going to have their own physical and chemical properties, but we can use their physical and chemical properties to separate them down into their component parts. Okay. Thank you for joining me today. I'm done.